So at the very beginning of this chapter, we talked about if a bond was polar or not. We talked about like polar covalent, non-polar covalent, that stuff. Now we want to apply that polarity to the whole molecule. And this is where, again, you need to be spatial and be able to draw these and think of these three-dimensionally. Because what happens is, remember, when you have a difference in your electronegativities, that means that atoms don't share nicely. And when they don't share nicely, when they don't share at all, then you are polar. One thing you have to be careful, though, is you can have polar bonds and not be polar overall. And the classic example of this is right here, CO2. So if you look at carbon being bonded to oxygen, they're not the same element. They don't have the same electronegativity. And so what you do is you look on your electronegativity chart, find who's higher, and that's who's pulling the electrons. So this arrow right here shows you that it's pulling electrons towards the oxygen. Excuse me. Same thing happens over here, and what happens here is, so you have two polar bonds. The issue is it's like a tug of war, and they're exactly the same. It's a mirror image of each other. So it's very symmetrical. It's three-dimensionally symmetrical. And what happens is overall, you actually cancel out. So if everything is completely symmetric three-dimensionally, and that's an important key, three-dimensionally, and everything cancels out, you're nonpolar. If something doesn't cancel out, then that's when you start getting polarity. And when you're polar, you're going to interact together differently than if you're nonpolar. This actually comes down to like why does oil and water not mix? Well, water is a very polar substance and oil is a very nonpolar substance, and they actually don't know how to interact with each other. And from bio and everything, you've heard all about how the cell membranes allow the things to pass through each other using polarity. Well, this is what they're talking about. And again, your lone pairs are typically a big reason that you would be polar. And unless you're exactly canceled out three-dimensionally, you're going to be polar. So here's another picture. Here, this is water. And I should add in that we do have two lone pairs here. So first you look at your bonds. And anytime you have lone pairs, they're pulling up and away. They want to get away. And then what you do is you look at your bonds and you see that, okay, oxygen and hydrogen are different. So you say, okay, who's more electronegative? Oxygen's more electronegative. And that's why I have arrows pushing up. And then when you sit back and look at this, you can see there's kind of an overall upward force on the molecule, which means that it's not being canceled. There's nothing three-dimensionally completely symmetric about it. And what you can see is these are a lot of electrons in the red up here. So what this is this is a polar molecule. So CO2 is a very nonpolar molecule, whereas water is a very polar molecule. There's just a couple examples in the next one here of polars and nonpolars. So here we have hydrogen chloride, and you can see they're obviously not the same atoms, so there is a polarity here, and you can see that there's a pull towards the chlorine, and it's not canceled, so it's polar. If you look at carbon tetrachloride here, you can see there is polar bonds, but you can see that three-dimensionally they totally cancel. So because they're all exactly the same and they're all pulling exactly the same, then you get that non-polarity. If one of these was something different, then it would be polar because they wouldn't be pulling the same. Boron trifluoride is kind of very similar. It has those three things pulling out completely symmetrically. Again, up here for ammonia, don't forget he does have, if it likes me, a lone pair. And you can see there's nothing to cancel the lone pair out, so he ends up being a polar molecule. And then last but not least down here, we have chloromethane. And you can see here that these guys would pull up. And then the important thing, though, is we have that chlorine that's very different than everything else. So again, it makes it not symmetrically three-dimensionality. There's nothing to cancel it out. The pull's up and over, and you actually are polar. And the last thing, these are just two more examples that we have of whether something's polar or non-polar. You're going to get a big chart, and you're going to work on these. And these are one of those things that, again, you have to work through them. You can't do one or two and think you have it. And you have to be able to wrap your head around three-dimensional, not just two-dimensional. Because when you draw it, sometimes it looks like it's going to be polar or non-polar or whatever. But then when you think about how it would cancel three-dimensionally, that's not how it works.